Okay, so for test review, the first thing I want to do is talk about the linear systems that you solve with eigenvalues and eigenvectors. There's going to be one where you have everything is real, like all the eigenvalues are real, all the eigenvectors are real, and then you're going to have one where you have to deal with complex numbers. Um, that one has a more complicated formula. I'm just going to make this test open book, so you can just look at this formula that's on page 391. I'm not going to give you any defective matrices, which is the ones where you have a repeated eigenvalue and then you don't have enough eigenvectors and then you have to do that much more complicated procedure to solve it. I'm not going to give you one like that. So let's try one. So here I have this system. So let me first write the matrix. And of course, we know that this all boils down to the eigenvalues and eigenvectors of this matrix. So minus lambda. So then I go 5 minus lambda, negative 1 minus lambda, plus 10. Right, so that would be lambda squared, and then I would have a plus lambda and a minus 5 lambda, so minus 4 lambda, minus 5 plus 10, so plus 5. And then I try to factor this, but I can't think of two numbers that multiply out to 5 and add up to negative 4, so I can use the quadratic formula. 4 plus, so this is a positive 4, because it's the opposite of that. Plus or minus 16 minus 4 times 1 times 5 over 2. So I've got that. So this is 2i. So when I divide it by 2, I get 2 plus or minus I. Okay, so we are doing the complex one. I figured I would, for the example, I would do a complex one because probably everybody knows what to do when everything is real. So I thought I would do the harder version. Okay, so let's find an eigenvector for, say, 2 plus I. So that means I'm going to set up a matrix. This is an augmented matrix with zeros on the right, and on the left I'm just filling this in, but I'm putting in the value of lambda. So I guess it's 2 plus I, so I would have 3 minus I, negative 5, 2, and then negative 3 minus I. Right? And I'm trying to solve, like I'm trying to solve this like matrix equation. In other words, like get this matrix in reduced row echelon form, or just echelon form, or whatever is good enough. So yeah, what are my options here? I could divide this row by 3 minus I. I could also, and maybe this is a better idea, I could switch the two rows and divide this one by 2. And I say that, I'm throwing that idea out there just because I would rather divide something by 2 than divide it by 3 minus I. But so maybe I'm feeling in a rare non-lazy mood right now, because I feel like maybe I should remind everybody how to divide by complex numbers. So let me take the hard road. I'm going to do rho 1 divided by 3 minus I. Of course, that's going to give me a 1 here. That one's not hard. 0 divided by anything is still 0. The big question is what goes here. But we can figure it out. It would be negative 5 over 3 minus I. I won't even write an equal sign yet. Because, of course, what you do is you multiply by the conjugate, 3 plus I over 3 plus I. And so on top, that's going to give me negative 15 minus 5I. And on the bottom, that's right. The bottom is like a difference of 2 squares. It's like a minus b times a plus b. So then it's a squared minus b squared. Which is 9 plus 1, which is 10. So let me cancel a 5 here. Negative 3 minus I over 2. Yeah. And now I have this, this comfortable feeling where I look at the two rows and clearly the second row is just double the first row. And this is what's supposed to happen because when you're finding an eigenvector, you really should have a 0 row eventually. So yeah, I'm just going to do rho 2 minus 2 rho 1. My goal is to make this a 0. Of course, this is also going to be a 0. That wasn't my goal, it's just what happens. Yeah, so what do? This one's free. So I'm going to write x2 is t, x1 is, I guess, to solve for x1 I would move this over so everything would be positive, but 3 plus I over 2t. So my eigenvector is 3 plus I over 2t t. And this is where I always say, like, this is every possible eigenvector. We just really need one eigenvector or a basis for the eigenspace. So this is a one-dimensional eigenspace. There's just t, there's no s. I can just say t equals 1 and call this the basis for my eigenspace. By the way, for the complex ones, typically we separate the real part and the imaginary part. Right, the real part of this is 3 halves, and then the real part of this is 1. The imaginary part of this is the 1/2 I, and there's no imaginary part here, so. Right, and yeah, the one nice thing when you have complex eigenvalues and eigenvectors is once you know one of them, you know the other one. In other words, we just found the eigenvectors for 2 plus I. Now the eigenvectors for the conjugate of that are just going to be the conjugate of this. In other words, I'm going to use this this vector for 2 plus I. So that means I can use the conjugate of this vector conjugate meaning I just switch this plus to a minus. That's my eigenvector for 2 minus I. It always works that way. So what do I do with this information? Now I'm just plugging everything in this formula. Oh, whoops. I guess I meant this formula. But I need another sheet of paper. So I'm basically done. I'm just assembling my answer here. So this gives me two linearly independent solutions. So basically I'm going to have a constant times this one plus a constant times this one. So let me just start writing this. C1 times the following. Right. So how does this work? The eigenvalues are, where does it say this? Yeah, so the eigenvalues are p plus qi and p minus qi. So for us, p is 2 and q is 1. So, right, when I go, and when I go down here, yeah, p is 2 and q is 1. A and B are the real part of the eigenvector and the complex part of the eigenvector, the imaginary part of the eigenvector, respectively. So my vector A is this 3/2 1, and my vector B is 1/2 0. So I'm plugging all that in. E to the pt. Actually, sorry. Let me start over. I just wanted to put that e to the pt on the outside of the parentheses. So e to the pt, and then it's a cosine qt, so that's 3/2 1. Cosine of qt, q is 1, so that's just cosine of t. Minus b sine qt, so minus, and this one was b sine qt, plus c2, I'm going to have my another constant times my next linearly independent solution, which would be, it also has an e to the pt on it. And then other than that, it's b cosine, so I'm going to go this cosine plus a sine. Yeah, so assembling your answer, it may feel like you have to look all over the place, and maybe that's true. You have to know P and Q and A and B, but all of that is just kind of looking back at what you already figured out. The big part of this is finding the eigenvalues and the eigenvectors of the matrix, and just remember that if it's complex, you know that they have this conjugate relationship. You're going to have two eigenvalues that are conjugates of each other, and if you find the eigenvector for one, you already know the eigenvector for the other because it's just the conjugate. Conjugate, once again, conjugate just means you flip the imaginary part. Okay, so let me stop this and start a new video with a new example.